Einstein said nothing can travel faster than light, and he was right. Nothing can move through space faster than light. But here's the loophole. Space itself has no speed limit. Space can expand, contract, or move at any speed. And in 1994, a physicist named Miguel Alcubierre figured out how to exploit this. He designed a spaceship that doesn't move. Instead, it warps space around it, contracting space in front and expanding space behind. The ship rides a wave of spacetime like a surfer on a cosmic wave. Relative to the space around it, the ship is stationary. But relative to distant stars, it's moving faster than light. This isn't science fiction. It's a solution to Einstein's equations. The Alcubierre Drive is real math, and NASA has a team researching it. The speed of light is the universe's ultimate speed limit. Light travels at 299,792 kilometers per second. Nothing with mass can reach that speed. If you try to accelerate closer and closer to light speed, your mass effectively increases, requiring more and more energy. To actually reach light speed would require infinite energy. It's impossible. This is a cornerstone of Einstein's special relativity, and it's been confirmed in countless experiments. Particles and accelerators approach light speed but never reach it. Photons travel at light speed because they have no mass. But for anything with mass, a spaceship, a human, light speed is a wall you can't break. This creates a problem for interstellar travel. The nearest star system, Alpha Centauri, is 4.3 light-years away. Even traveling at light speed, it would take over 4 years to get there. And we're nowhere near light speed. The fastest spacecraft humanity has ever built, Voyager 1, travels at about 17 kilometers per second, roughly 0.006% the speed of light. At that speed, reaching Alpha Centauri would take over 70,000 years. The Milky Way galaxy is 100,000 light-years across. Reaching the other side at current speeds would take billions of years. The observable universe is 93 billion light-years in diameter. Forget it. We're stuck in our tiny cosmic neighborhood, unless there's a loophole. And there is. Einstein's theory doesn't just say objects can't move faster than light through space. It also says space itself can expand or contract. In fact, space is expanding right now. Distant galaxies are moving away from us faster than light, not because they're traveling through space at that speed, but because space between us and them is expanding. The galaxies aren't breaking the speed limit. The racetrack is stretching. This is cosmological expansion, and it's been observed and measured. So space can move faster than light. That's the loophole. In 1994, Mexican physicist Miguel Alcubierre was a grad student thinking about Star Trek. He wondered if warp drive, the faster-than-light propulsion system in the show, could actually work within the laws of physics. He started playing with Einstein's field, equations, which describe how mass and energy curve spacetime, and he found something remarkable. A solution where a bubble of flat spacetime containing a spaceship is surrounded by a region where space contracts in front and expands behind. The ship itself doesn't move relative to the space inside the bubble, but the bubble moves through space by surfing a wave of spacetime distortion. To an outside observer, the ship appears to travel faster than light, but technically, it's not. It's stationary inside its bubble. Space is doing the moving. Imagine you're standing on a moving walkway at an airport. You're not walking, but you're moving forward because the walkway is. The Alcubierre Drive is like that, except the walkway is space-time itself. The ship contracts space ahead, creating a downhill slope. It expands space behind, creating an uphill slope. The ship slides down the slope, carried along by the geometry of spacetime. Einstein's equations allow this. There's no law of physics being violated. You're not moving through space faster than light. Space is moving you. Alcubierre calculated that a warp bubble like this could, in principle, move at any speed, 10 times light speed, 100 times, even faster. The ship inside experiences no acceleration, no g-forces, no time dilation. From the crew's perspective, they're sitting still. Outside, space is doing all the work. This would allow interstellar travel without relativistic effects. You could travel to Alpha Centauri in weeks instead of millennia. You could cross the galaxy in years instead of lifetimes. You could explore the universe. But there's a catch. Actually, several catches. The first is energy. Alcubierre's original equations required an absurd amount of negative energy, more than the mass energy of the entire observable universe. Negative energy is not regular energy. It's exotic matter with negative mass energy density. In quantum field theory, negative energy is possible in tiny amounts. The Casimir effect demonstrates this. Two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force because the vacuum between them has less energy than the surrounding vacuum. That's negative energy. But the amount required for an Alcubierre drive is astronomical. We're talking Jupiter mass quantities of exotic matter. We don't know how to create it, store it, or manipulate it. However, in the decades since Alcubierre's original paper, physicists have found ways to reduce the energy requirement. By tweaking the shape and thickness of the warp bubble, the energy requirement drops dramatically. Some models now suggest you might only need the mass energy of a small spacecraft, like Voyager, converted into exotic matter. Still impossible with current technology, but no longer absurdly impossible. It's gone from never to not yet. The second problem is causality. Faster than light travel allows time travel. If you can move faster than light in one direction, you can, under certain conditions, return to your starting point before you left, creating a causal loop. This is a consequence of relativity. Different observers in relative motion disagree on the order of events. If you move FTL in one reference frame, you can move backward in time in another. This leads to paradoxes, the grandfather paradox, causal loops, violations of cause and effect. Some physicists argue that any FTL technology is inherently a time machine, and if time travel creates paradoxes, then nature must forbid FTL travel. Others argue that chronology protection mechanisms, quantum effects, or unknown physics might prevent paradoxes. Or maybe many worlds interpretation resolves them. Or maybe time travel is possible, and we just have to accept the weirdness. The third problem is navigation and control. How do you steer a warp bubble? Inside the bubble, you're causally disconnected from the outside. You can't see where you're going because light from ahead is trapped outside the bubble. You can't communicate with the outside. You can't slow down or stop without collapsing the bubble. Some models suggest the bubble, once created, might be impossible to control from inside. You'd have to set your destination before engaging the drive, and then hope nothing is in your path. Crashing at faster than light speeds into a planet or star would be catastrophic and unavoidable. There's also the problem of energy buildup. As the bubble moves, it might accumulate particles and radiation on its leading edge. When the bubble collapses, all that energy could release in a deadly burst, incinerating anything in front of the ship. Not ideal for arriving at a new solar system. Despite these problems, NASA took Alcubierre's idea seriously. In the early 2010s, physicist Harold "Sonny" White at NASA's Johnson Space Center led a small team researching warp drive feasibility. They explored modified warp bubble geometries and even claimed to detect tiny, spacetime distortions in lab experiments using high-voltage capacitors. The results were controversial and not replicated, but the fact that NASA funded the research at all shows the idea isn't dismissed as pseudoscience. It's speculative, yes, but it's grounded in real physics. Other concepts related to FTL travel exist. Wormholes, shortcuts through spacetime, are another solution to Einstein's equations. If you could create or stabilize a wormhole, you could step through it and emerge light years away instantly. But wormholes also require exotic matter to stay open. And they might be time machines too, with all the same causality problems. Quantum entanglement offers instantaneous correlation between particles, but you can't use it to send information faster than light. No communication theorem prevents that. So entanglement isn't a communication or travel method. Some theories beyond general relativity might allow FTL. In certain versions of string theory or quantum gravity, the light speed limit might be modified at high energies. Maybe there are extra dimensions we could tunnel through, bypassing normal spacetime. Or maybe spacetime itself is emergent, and at a deeper level, faster than light connections exist. These are highly speculative, but they keep the door open. Interestingly, some UFO enthusiasts point to the Alcubierre Drive as evidence that alien visitors might use warp technology. If other civilizations are millions of years ahead of us, they might have solved the exotic matter problem. They might have built warp-capable ships. This is pure speculation, of course. We have no evidence of alien visitors, let alone alien warp drives. But it's a fun thought experiment. If you were an advanced civilization wanting to explore the galaxy, warp drives would be one of the few physically plausible ways to do it. There are also proposals for warp drive light, not true FTL, but significant fractions of light speed using related concepts. By creating small space-time distortions, you might reduce inertia or enhance propulsion efficiency. This wouldn't break the light barrier, but it could make sublight interstellar travel much faster and more practical. Some researchers are exploring this as a nearer-term goal. Even reaching 10% light speed would allow missions to nearby stars within a human lifetime. Then, there's the philosophical question: should we pursue FTL travel? If it leads to time travel and causality violations, maybe it's too dangerous. If it requires exotic matter we can't control, maybe it's too risky. But humanity has always pushed boundaries. We split the atom despite the dangers. We edited genes despite ethical concerns. We built AI despite existential risks. The drive to explore is fundamental. If there's a way to reach the stars, we'll try. And if warp drives are possible, even barely possible, someone will attempt to build one. What would a warp-capable civilization look like? Interstellar travel would become routine. Colonization of exoplanets would be feasible. Trade, communication, and conflict between star systems would emerge. The galaxy would shrink. The timescales of history would compress. Decisions made on one planet could affect another within years, not millennia. This is the stuff of science fiction, but it's rooted in real equations. The physics allows it. The engineering is the hard part. Some physicists remain skeptical. They argue that any technology requiring exotic matter is inherently implausible. We've never observed exotic matter in macroscopic quantities. We don't know if it can exist stably. We don't know if it can be manipulated. The energy requirements, even reduced, are staggering, and the causality issues are unresolved. Faster-than-light travel might be mathematically possible, but physically forbidden by some deeper principle we don't yet understand. Maybe the universe has built-in protections against FTL. Maybe spacetime has safeguards, but others remain optimistic. They point out that every major technological breakthrough seemed impossible before it happened. Heavier-than-air flight, nuclear energy, quantum computers. Each violated common sense and required leaps in understanding. Maybe warp drives are the same. Maybe in a century or 5 centuries, we'll look back and laugh at how primitive our 21st century technology was. Maybe starships with Alcubierre drives will be as common as airplanes. Or maybe FTL is truly impossible, and will remain forever bound to our local corner of the galaxy, sending messages and probes, but never traveling ourselves. Either way, the Alcubierre Drive stands as a testament to human creativity. A grad student, inspired by a TV show, found a loophole in the universe's strictest law. He didn't break physics, he bent it. And in doing so, he gave us a map, a possible route to the stars. Whether we can follow that map remains to be seen. But the map exists, and that, in itself, is extraordinary. Because it means faster-than-light travel is not forbidden by the laws of physics. It's just really, really hard, and humanity has a history of doing really hard things. So maybe one day, centuries from now, a ship will engage its warp drive, space will contract and expand, a bubble will form, and inside that bubble, a crew will sit calmly as the stars blur past. They'll think of Alcubierre, they'll think of Einstein, and they'll smile. Because they didn't break the speed limit, they just found a better road.